So, welcome from my side. I'm from the Research and Innovation Department in Festo in Bergheim, and I'm in the team for Applied Artificial Intelligence. And within this team, I have specialized on the integration of AI solutions into factory automation. Today, I would like to welcome you to my talk about the deployment of machine learning models in automation, and roundabout in the next 20 minutes, I will give you a short overview about this topic. Let's start with today's agenda. First, we'll discuss the benefits of using machine learning in automated systems and the potential it offers to many industries. Next, we'll focus on the machine learning itself and the focus I want to set for today. Then I'll describe common ways for the deployment of machine learning models and how this could be used in this context, followed by the options to link PLCs and deployed machine learning models. I will end with two practical examples, how this can be achieved with today's component. And yeah, I'll directly start with the why. Why should we use machine learning in automated systems? First, I want to mention things that are already common today, like condition monitoring or predictive maintenance. For such applications, especially anomaly detection and also anomaly classification, we already have Festo AX in our portfolio here at Festo. Then secondly, I think it's the next logical step to integrate AI solutions into the automation technology. And my expectation is that in the coming years, it will be quite normal to add AI features to our classical factory automation. Then we have tasks that can't be solved with classical PLC programming. For example, in advanced robotic skills, for example, if you want to grip unknown objects or stuff like that. And finally, we have a wide range of new automation applications that have not been automated so far. For example, the controlled environment agriculture or the lab automation, which is characterized by a much less deterministic environment compared to our factory automation that we know from our past. To narrow the focus of today, let's first look at the development process of AI solutions. These often follow the CRISP-DM, the cross-industry standard for data mining, and they consist of the business understanding, the data understanding, data preparation, which is a really big task, the modeling, and the evaluation. Or in other words, the entire path from the question to be answered via the data and the selection of the type of model we use for this problem through the training to the finished machine learning model. But today's talk is more about the right side, with the deployment, the integration, the inference, as well as the monitoring and management of such solutions. Or in other words, how can I deploy and maintain a machine learning model in an automation environment? The setup and the consideration also plays an important role. The focus of today is on a bidirectional connection between a PLC runtime, for example, codices, and a machine learning model like TensorFlow, PyTorch, ONNX, or scikit-learn. Especially not in focus today are machine learning models that are directly integrated or fixed within an embedded system, for example, as part of a firmware. For example, to control or monitor individual automation assets like drives or walls. And also not in focus are solutions where machine learning models are executed directly within the PLC runtime, as there are only a few tools available for this, and the solutions tend to be less flexible and difficult to maintain. However, as we will see also later in the examples, this does not mean that the PLC runtime and the machine learning model can run on the same computing hardware. Now, there are different ways to serve machine learning models. These range from simple code running on a machine over containers and runtimes up to inference engines on the right side. While on the left side, we have more the lightweight solutions. Towards the right side, we have more features, more possibilities regarding the scalability, the logging, the monitoring, and the integrated security we get with those solutions already included. In the following, we'll take a look at the structure, the advantages and disadvantages, as well as the possible application scenarios for the individual options. First thing is the deployment as code with the required dependencies on a machine without using any special tools for the deployment. Very simple, very basic. The advantage is, of course, the high flexibility. We have no restrictions and we can do whatever we like. Also, it's very lightweight as we have no dependence or no overhead of any kind in this scenario. Also, there are no special skills required, at least on the first glance. Because the disadvantages are that there's much manual work to do. For example, there are no helping tools to implement a suitable API for the machine learning model. We have to implement access and security measures on our own. Also, the same goes for logging, monitoring, and much more. Also, there are no tools for the maintenance of the model, which could lead to challenges. And you have the typical, it works on my machine problem. I think there's later on a talk on this topic, especially because the execution environment and the dependencies are hard to describe. Taking all this into account, you might come to the same conclusion as me, that this kind of deployment can't be recommended. Maybe during the deployment, but also in this, maybe during the development, but also in this case, you might use development containers or stuff like that that will help you to have a higher quality on your code. An example for this kind of deployment is very simple. Just take your favorite programming language together with your favorite framework for machine learning, put your code on a machine, on a server where you want to execute it and run it there, and you're finished. The second type is the deployment using a container virtualization to pack your machine learning model together with all the required dependencies and a suitable interface. With this approach, you still have a high flexibility because you can still do whatever you want inside of your container. Also, the containers are still quite efficient regarding the required resources. Plus, you get all the common benefits from containerized solutions. For example, the well-defined environment, the portability, and also the scalability. The disadvantages are that there is still a lot of manual work. You have to learn how to create and serve your containers, and the debugging of containers might be a bit more challenging. I would recommend this type of deployment during the development, also for prototypes, as well as for small to medium scale deployments. To use this type of deployment, you could use Docker or Kubernetes to create and serve your containers. Also, and this might be interesting for people that are not familiar with Docker, there are machine learning libraries that are able to directly export containers, such as MLflow or BentoML. The third type of deployment is to use a runtime as an execution platform for your machine learning model. The advantages are the simplicity, as most runtimes are well documented and easy to use. Furthermore, they are often optimized for execution speed and also for handling larger amounts of requests. Also, they provide features to automatically generate a suitable API for your machine learning models, and you have tools for monitoring and logging already included. On the other hand, runtimes are often bound to specific frameworks like PyTorch or TensorFlow. Or the models must be converted to a neutral format like ONNX. The debugging within the runtime can also be a bit challenging, and the API format can't be changed or influenced by the extent you have if you create your containers by your own. Most runtimes only support HTTP requests or a gRPC interface. This approach can be recommended for small to medium scale deployments in combination with container virtualization, also for large deployments. Examples to mention are the ONNX runtime that is available for nearly all common programming languages and uses the neutral model format ONNX, as well as TorchServe and TensorFlow serving, which are specific for PyTorch or TensorFlow models. Now we come to the most featured, but also most heavy option to deploy your machine learning models, which is the deployment with an inference engine. Beginning on the left side, the basis is the base for such a system is a Kubernetes cluster with the inference engine installed on it, which deploys the containerized machine learning models. Then we have a common gateway to access all our deployed machine learning models. And on the right side, we can see that most inference engines come packed with a large set of features for the management of your deployments, such as monitoring, logging, versioning, updating, and also scaling. And one special thing is that you can link different models together, which is helpful to separate pre and post processing from the actual model, and also to implement ensemble learning, where you have several models running in parallel, and then have within the post processing the decision for the best result. The advantages of this approach are the large set of included features you get out of the box with the installation, the support of all common machine learning models, so it's not specific to a special type of model anymore, and it's also very simple to create your own extensions. Also, the mechanisms for rolling updates with no downtimes and scaling of solutions is beneficial for especially large deployments. On the other hand, inference engines have a high resource utilization, so you might not want to have such a thing on your embedded device. It tends to be a bit more complex, and it requires a bit of a steep learning curve to use such an inference engine. Therefore, the recommendation to use the inference engine is for medium to large scale deployments, or for scenarios where you have heterogeneous models, for example, PyTorch model running directly next to a scikit-learn model, for example. Examples for inference engines are Kserve, which is formerly known as Cave Serving, or Seldon Core. And a very beginner-friendly option is the inference engine Yatai, which is an optional part of BentoML. Now we have covered quite some ways to deploy a machine learning model. Let's now have a look on how to connect them to the POC. To bring together our POC with the deployed machine learning, we need to find a common interface, of course. There we have a lot of options on the POC side. And depending on our use case and focus, the most interesting are often the MQTT or the HTTP interface. On the machine learning side, most auto-generated APIs, I already said that, are using HTTP or gRPC. And of course, if you don't use auto-generated APIs, we're free to implement whatever is suitable for our application. In most cases, I would recommend to use HTTP-based APIs on the machine learning side, as they're very universal and can be directly accessed by nearly all types of devices. If the use case requires MQTT or other protocols on the PLC side, a middleware can be considered to translate between the different protocols. And with this, the more theoretical part of my talk is over, and now I want to bring a bit more a practical view on this topic. And for this, I brought you two examples. So in this first example, this should be a video. Okay, it doesn't play. In the first example, we see an inline quality monitoring system that sorts between good, defective parts and parts for rework. The parts are filmed by a camera, and as soon as the light barrier somewhere here is broken, the PLC sends a trigger using an HTTP request. A middleware then combines the trigger signal with the current frame of the camera and forwards this request to our Inference Engine, where the machine learning model handles this request. And as soon as a result is available, it's sent back to the PLC, and the motor is moved to the corresponding position. What we can see here is a complete end-to-end solution with a PLC and a machine learning model directly integrated into our process. And in the second example, we can see a gesture control for a handling system. A camera is filming the user, and the images are directly sent to a neural network that is executed within a container. And in this case, we use a TensorFlow model from the MediaPipe project that can recognize hand poses from 2D images. And the determined positions are then sent via MQTT to a soft PLC running on the same control hardware. So this is what I mentioned earlier. Here we have the case that the machine learning model and our soft PLC are running on the same hardware platform, which gives us a lot of flexibility. And the soft PLC processes the data and transmits the position data to the line portal. And how this looks in action, we hopefully see on the next slide, while I've embedded another video. Yeah, it's running. Perfect. So you can see the camera right over here. It's integrated. The processing all on this controller, and the position data is forwarded to the line portal. We also integrated user interface, a small user interface, and we also detect for anomaly using Festo AX. And with this, I want to end my presentation. I thank you for your attention, and I'm already curious about your questions.